morning, everyone. I'm Vishal Bhalla, and first of all, I would like to thank Nick for the wonderful insights on how his project aligns with the long-term autonomy. My topic is prior affordance understanding with relational learning for human-safe action planning. Before I begin my talk, a short introduction about myself. I'm basically a master's student at Technical University of Munich. I'm doing my master's in informatics. My major focus is in artificial intelligence and cognitive robotics. I've applied a wide range of machine learning algorithms across the security, medical imaging, and robotics domain. And in particular, I'm interested in applying AI, NLU, and statistical relational learning, which is part of the project which I did now in the robotics domain. And I can be reached at my email address, and I'm always looking out for collaborating on novel projects. So let me begin with the agenda for the talk. So I start off with the motivation or the overall goal, what is the reason behind this project, and what we are trying to achieve. Then the problem formulation, how we try to achieve this, the prior work done in this field, the limitations and how we overcome them, the two major technologies used, and the two major phases, that is training and evaluation, and especially the selection of corpus for each of these phases. And then finally, I talk about the evaluation results, especially in terms of scalability and how it aligns with the goal or the for this conference, that is long-term autonomy. And finally, to conclude the talk with how this project could be extended further upon. So, yeah, so basically, cognitive robots still lack what we call as common sense knowledge. So, if an object is placed in front of a robot, it still doesn't know what it can do with it. So basically, this is called as affordances. They encode the relationship between actions and objects. That is, it gives an understanding of how a particular object can be acted upon. So the current state of art is at potential risk because it uses affordances are obtained by sensory motor exploration with reinforcement learning, and this cannot be used as an initial estimate. So the crux of this project or this paper is we provide an initial or safe estimate of the task. So if you see in this example, if an apple is placed in front of a robot, it doesn't know what can do with the apple. So if given a learning, in this project we are using text-based learning. The text could be like cut apple, pick apple. So then it knows that an apple is cuttable and an apple is pickable. So these are the affordances that can be learned. So in this way, we can give some prior knowledge to the robot. So how this looks like in the overall goal we are trying to achieve. If you see on the top left, we do the training part. In the training, we start off with some WikiHow, this is like a website which we do web crawling on. So the text looks like this. Clean the floor as the final step, follow up dusting by cleaning the floor. So with this text, we do some grammar dependency extraction. So one such dependency would be a direct object between the verb cleaning and the object floor, and similarly a noun subject, which is a relationship between the person and us. So after extracting all these dependencies, we pass it to a relation robot that a person can dust. A floor is cleanable because we get probabilistic estimates of the different tasks based on the rules which we define. So the problem formulation is basically an ability-modality processing. What is ability-modality processing? Is basically we are trying to extract potentiality relationships which can be represented by a joint probability distribution of SVO tuples, that is subject, verb, object tuples. The challenges in doing this ability-modality processing include passing the input text using Stanford type dependencies, then doing the SVO tuple analysis, then doing the relational learning using MLN, that is Markov logic networks, and finally to decide whether the object is active or passive. So now I come on to the prior work done in this field. So the related work in this field can be looked upon from three different viewpoints. First would be the mapping between affordances and language constructs. So two such papers, they use this. But in one of these papers, they do the opposite thing. That is, they use affordances to get the grammar dependencies, that is adjectives, nouns, and other relations. But we wanted the opposite. The second paper does some mapping, but it doesn't talk about how the initialization parameters are populated from the ontologies. Another viewpoint is using type dependency extraction for semantic characterization. But in this paper, there is no focus on the verb-noun pairs, which we are interested in. The last viewpoint is basically from using Markov logic networks for NLP in robotics, that is natural language processing in robotics. But again, in this, there is no grammar feature analysis. And in another paper, it uses only inference on missing affordances. So the closest work which was done in this regard is basically a concept-only paper, which provided the initial motivation for this project. Another work by Niga and other authors, they do this mining of affordances, but they don't focus on the scale of text mining, which is basically what we're trying to achieve here, and nor the application of affordances. So I start off with the two major technologies used in this project. First is Stanford type dependencies. So what are they? They provide basically a straightforward description of the underlying text or the grammatical relationships for automatic text understanding. And why are we selecting only N subject, that is noun subject, and D object, that is direct object, out of the many different relations in the text? So for example, there could be prepositions, auxiliary verbs, and other relations. But these two reliably represent the potentiality relationship which we are interested in, which I talked about in the previous slide. Also, they represent, they give a lower passing error rate in comparison to other complex grammatical relations. The second important technology used is MLN, Markov logic networks. It's basically a very powerful framework combining statistical, that is using Markov random fields, and first order logic. So probability of a world X could be given as the, if you see inside the exponential, it's the sum of all the weights of any formula with the true, multiplied with the true groundings, and then we divide it by this Z, which is called as a partition function, so that we normalize and get a probability value between 0 and 1. So in this project, we started off first with Alchemy. That is a tool, MLN tool, but it doesn't scale well. So then we shifted to Tuffy. It scales up weight learning and statistical inference using internally an RDBMS. There is another tool now called Felix. These two tools are from Project Hazy. That also helps in large-scale inference. So the two major phases are basically the training and the evaluation phase. So the training phase comprises of two parts. The first part is basically web crawling, and the second part is the relational learning part. So the important question was to where do we start? What corpora do we take for this web crawling? So we could have taken, for example, Wikidump, but Wikidump contains too much of figurative text. So why not Wikidump and why something else? What is the requirement? So the requirement is basically to have technical text in the form of instructions. So ideally an ICRA manual. So if you want like how to build a desk, how to build a table, that would be excellent. So we came across wikihow.com, which is basically a user manual, which has user manual like text on how to do the daily tasks. So we web crawled or scraped the text out of the links. And as a pre-processing step, we also lemmatized the inflected word forms so that we reduce the error, and it's also good for comparison. So for example, the word move, moving, moves, all would map to the root word move. And in the second part, we passed, after doing this, we set up the relational learning part, which comprises of, again, two parts, weight learning and inference. So in the weight learning part, we defined what we call as first order logic rules or predicates. So in this case, we were only interested in the direct object and N subject. So we had this D object N subject notation where DE is the verb. and object is the noun. Same with the end subject notations. Another important thing to note here is the plus notation, which basically means that we are expanding on all possible groundings. We are grounding on all the scene data, all the nouns available in the database. And then we perform an MCSAT inference, which is an Markov chain Monte Carlo inference algorithm to estimate the marginal probabilities. So then we came to how do we evaluate our system. So what should we select as an evaluation corpus? So we chose the CAD 120 dataset, which is basically 120, which consists of 120 RGB videos of daily activities. It consists of 10 high-level activities. So these include making cereal, cleaning objects, arranging objects, and so on. And they constitute of 12 object affordance labels, that is reachable, containable, openable, and others. One more thing which we did was for comparison, was to use the manually annotated video data and mapped it to this verb, direct object form, which we were getting in the training phase for comparison. So here are the evaluation results. You have the number of words. So basically this graph is basically an object passivity rate against the WikiHow word coverage. So at the start, if you see, as the number of words were less, the out of vocabulary rate was very high. That is, many affordances, labels, and were not even covered. So we gradually increased the word coverage. So as we increased the word coverage, the out of vocabulary rate dropped to a minimum value, and also the classification rate, which was very low, raised to a maximum value, and also the misclassification rate dropped to 0. So basically, what we understand, what this graph basically helps us confirm is basically more the words, more would be the knowledge acquired, and hence more would be the classification accuracy, and less would be the out of vocabulary text. So to conclude the talk, basically we started off with what we call as technical text, that is instruction-based text, which we are using for the training phase, which we used from wikihow.com. Second important thing is we use SVO, that is subject, verb, object tuples, and these tuples are enough to represent the information to model potentiality relationships which you are interested in, and we are not using other complex grammatical relations in text. So these are the two main underlying assumptions which we considered in this project. Then we evaluated WikiHow training text against the ground truth from CAD 120 dataset, and what kind of comparison we did is not just on the number of, if you see previously, it's based on the number of links or the number of words. So we did the comparison on different WikiHow links for both qualitative and the scalability analysis which we were interested in. So we increased the number of links for scalability. So the results we got were optimal convergence rates for entity coverage, that is, as the links were increased, the coverage was more. And also the classification rates were acceptable at the end. So, and this verifies the fact that we are not attributing as insecure something that is safe. That is, if an object is passive, it is classified as passive and not active, and vice versa. The code and all the evaluation results for different WikiHow links could be seen in these two links. One more important thing in the WikiHow links were we used a random subset of 46 links and then used like 3, 5, 10, and so on, and we did it like for 5 different iterations so that we cover different set of affordances. So finally, how could this project be extended upon further? So we could scale to a larger training corpus. We just used like 100 different links this time, around 30,000 words from wikihow.com. But this could be easily scaled to a larger training corpus. And what would this give us is basically maximum word coverage and minimum misclassification rate. Another important thing is we are using a relational learning based approach, that is market logic networks, but it would be interesting to compare this current approach with traditional naive bias based approaches. Another important thing is to increase the classification rates by increasing the rule set. The rule set, if you remember, was just a simple D object, N's object, and we were just expanding on all possible nouns. But if we could increase the rule set, especially by exploiting the underlying semantic structure of text. So one important thing which I would like to highlight here is this Friday, in fact, Google released its tool on TensorFlow, deep learning tool on TensorFlow called SyntaxNet, which is now the state of art. Instead of Stanford parser, it achieves like 94.24% accuracy on web-based data. Since we are also using web-based data, wikia.com, that would be interesting to try out here. So instead of using Stanford parser for parsing, maybe another model could help us exploit the underlying semantic structure of text. So that would be an interesting extension of this project. Lastly, the rule set, as I said, was simple because we wanted to achieve scalability, and we are just modeling whether an object is active or passive. But it would be interesting to know if we could model the likelihood of different possible actions on a given object. So we are not just interested whether an apple is active or passive object, but also what kind of actions can be done on an apple. For example, it is pickable, cuttable, and so on. So that lies that could be one possible future. And yeah, do you have any questions?
I didn't really get the long-term aspect of it. Can you just sort of explain how long-term
yeah, so
so what was the long-term aspect?
So so we started off with a few links, and basically what we are trying to achieve and how it aligns with this workshop or the long-term aspect is more the number of words, the more would be the autonomy, or more would be the knowledge acquired by the robot. So here we just use like 30,000 words. So if we increase more, that would be like in the long-term aspect of it, we would achieve autonomy, and not just by this simple case of whether an object is active or passive, but also on the future work, which could be to model the likelihood of different possible actions on an object.